Hello, welcome everyone. In this lecture, we're going to study electrical distribution systems and gate model questions on distributors. So what is a distribution system? It is a part of power system network which taps electrical energy from the major substation in the outskirts of a city, town, and distributes power to the loads like industries, home, commercial buildings, municipal load, irrigation loads, etc. So a distribution starts basically from the outskirts of a town or a city where a major electrical substation is present. From there, the electrical energy is being tapped and being distributed to the different loads like industries, household loads, commercial buildings, apartments, etc. So basically it distributes the electrical energy to the customers. Distribution system usually employs equipment like transformers, circuit breakers, fuses, isolators, etc. So what makes a good distribution system? A good distribution system should have two properties. What are those? The first one is it should provide proper voltage profile to all the connected customers. That means all the customers who are connected to the distributor should get proper voltage. That means the voltage fluctuation should be minimum. Understand? And second important feature of a good distribution system is 24/7 distribution system should be able to provide electrical energy to the customers. So these are the two properties of a good distribution system. Next we'll see few definitions. So the first one is feeder. What is a feeder? A feeder is an electrical conductor which is not tapped in between, for power. Current throughout the feeder remains constant. So a feeder is an electrical conductor which starts from one substation and ends at another substation. In between the feeder, nobody taps it for electrical power supply. Okay, so current through the feeder is constant. Okay, so in distribution system, feeder connects the substation to the area where the power is to be distributed. Next, very important point. The main consideration in the design of feeder is the current carrying capacity, because since feeder almost carries the same current, the main design criteria for the feeder is the current carrying capacity. Okay, since the current in the feeder is constant, the feeder has constant current density. So what is the main design consideration for the feeder? The main design consideration for the feeder is the current carrying capacity or current density. Next is distributor. What is a distributor? A distributor is an electrical conductor from which tappings are taken and supply is provided to the customers. The current throughout the distributor is not constant because tappings are taken at various places along its length. So distributor is the electrical conductor from where the customer taps the electrical energy. So the current through the distributor is not constant. It varies because there are so many taps along the distributor which draws the electrical energy in the form of current tapping. Now, the main consideration in the design of distributor is voltage drop. Okay, so you have to design a distributor such that the voltage drop along the distributor is minimum, so that all the customers who are connected to the distributor gets proper voltage. Okay, the size and the length of distributor should be such that the voltage at the customer terminals is within permissible limits. Okay, limits. What is the permissible voltage fluctuations is plus or minus 6% of the rated voltage. Okay, this figure can vary from one state to other. In general, if you have the voltage fluctuations within plus or minus 6% of the nominal voltage, then we say that it is having proper voltage profile. Okay. For example, you are a single phase customer. Your nominal voltage is 230 volt phase to neutral. So what is the right voltage for you? Proper voltage for you is, it should be 230 volt plus or minus 6%. So this value boils down to 218 volts to 242 volts. So if you get the voltage in this range, your voltage profile is good. Similarly, if you are 11 kV customer, that means your voltage should be within the plus or minus 6% of the 11 kV. So this is the example for the proper voltage profile. What is service mains? Service mains is a small cable which connects the distributor to the consumer terminal. So the cable from which is connected to the distributor to our metering panel in our household, it is called a service mains. Understand? So one important point in the slide is, the main consideration for the design of distributor is the voltage drop. Don't forget. Okay. Now let us see an example of a distribution system. Okay. Let us assume a 400 kV transmission line is starting from a generating station and it is reaching the outskirts of a city. What is the voltage of the transmission line? 400 kV transmission line, which is originating from the generating station. It is terminating at a substation in the outskirts of the city. This substation steps down this 400 kV to 132 kV. Okay, this is a step down substation or a major substation in the outskirts of the city. From this, different feeders, 132 kV feeders, go to different strategic locations of that city. If there is a very big consumer, an industrial consumer who wants a bulk load, so he can directly tap 132 kV industrial customer. So he is tapping energy directly at 132 voltage. So like this, different 132 kV feeders are going to different locations of the city. So within the city, again there will be substations which will step down this 132 kV voltage to, this is a substation within the city which steps down 132 kV to 33 kV. Okay, again this 33 kV feeders will again go to different strategic locations in that particular area. If suppose there is a medium scale industry who is directly taking, suppose medium scale industry which is taking supply directly at 33 kV, or there may be a big commercial complex or a mall or commercial complex which is tapping power at directly 33 kV, or a very big housing community which has its own internal substation, a big gated community. So like this, different, so there are different kinds of loads in that area which directly taps at 132, which directly taps the supply at 33 kV. Again this 33 kV is stepped down to one more smaller substation would be there which steps down this 33 kV to 11 kV, from where the 11 kV feeders will go to the different locations in that region. A big apartment can directly take 11 kV supply. a small industry, small scale industry can directly take 11 kV supply. Like this, different customers will take the 11 kV voltage. Okay. Now, for the household customers, suppose this is a 11 kV feeder that is going into one street. Again, there will be a distribution transformer which steps down this 11 kV to 415 volts. So where 11 kV is a delta, 415 volt is a star. From there, the distributor goes, and to this distributor, the customers are tapping the power supply. So this is an overall view, overall single line diagram of a radial distribution system. Understand? So here one thing I want to stress is that there is no clear-cut distinction of a voltage at which the distribution starts. In a big city, the distribution can start at 132 kV. Suppose it is a medium level town, then directly the transmission line that is coming from the generating station can be 132. So directly the distribution can start at 33 kV. So there is no clear-cut distinction of the voltage at which the distribution starts. In case of a city, it can be the 132, very big city, 132 kV. In case of a middle level town, it can be 33 kV voltage. Or in a small village, the distribution can be start at 11 kilovolt. Now you can see in the figure, this is the distribution transformer which is present in the corner of your street. Distribution transformer where the input is delta connected, where the primary or HT connection is 11 kV which is delta connected, and the secondary is star connected, and the star point is grounded. So what is the voltage of LT? LT is 415 volt. Understand? Now the neutral starts from the secondary of the distribution transformer. The neutral starts from the star point of the distribution transformer. The primary in the distribution transformer is majorly delta connected and the secondary is star connected, because when we do star connection, then only the neutral will come into picture. Suppose if you are a single phase customer, the tapping is provided from one phase and one neutral, and it is given to the single phase customer. Suppose he is a three phase customer. Three phase customer is a person who is having more load. Suppose every bedroom has a AC, geyser, bathrooms have geyser. So if you take single phase supply in such situations, the voltage drop will be more. You will not get proper voltage. That's why when the load of the customer is more, then you have to give him three phase supply. Okay. So these are the wires that are connecting the conductors that are connecting the distributor to the customer are called service mains. Service mains. Understand? So here in any distributor, if you only have the source at one end, what is the practical problem? The customer who is connected, who is tapping the supply near to the DT will have high voltage, and definitely the customer who is tapping supply from the far end will have low voltage. Okay. The problem with this kind of distributor, this is called radial distributor, where there is distributor is fed from only one end. The customer who is near to the distribution transformer, near to the source, has high voltage. The customer who is at the far end of the distributor will have low voltage. Okay, so they will not get a proper voltage. Next, the types of distribution systems classified basis on the nature of current. DC current distribution systems and AC current distribution systems. Because nowadays all the generation, transmission and distribution is done by AC systems only. So DC distribution systems are very rare. Only for exclusive applications where you have DC motors and DC loads, you need to have a DC distribution system. Okay. So since the AC system is universally adopted, electrical distribution in AC is quite simpler and economical when compared to the DC current method. DC distribution is only used in special applications or in industries where the DC motors are running or where specific DC loads are there. Otherwise, what they do, if you have a small DC load, you have a battery charger or a rectifier unit that will convert AC to DC, and from there the DC is distributed to the small loads in the industry. They have their own rectifiers which convert AC to DC, and from the output of that rectifier they will distribute the power to their DC loads. Okay. Next, according to the scheme of connection, the distribution systems are mainly classified as radial system, ring main system and interconnected system. So depending upon the scheme of connection, the distribution systems are classified as radial, ring main, and in radial system of distribution, separate feeders radiate from single substation and feed the distributors at one end only. Okay, so the simple definition boils down to there exists one and only one path of electrical supply from major substation to the customer in a radial distribution system. Okay, so suppose if you observe this single line diagram which we have built earlier, see, from the major substation of 132 kV by 33 kV here to the customer, there is only one and only one path of electrical supply. If there is any interruption or disturbance in this path, the customer will not get the supply. So this is a radial distribution where there exists one and only one path between the substation and the customer. Second point which I want to tell, if you look at this radial distribution system, all the feeders from the respective substations are emanating in the form of rays to different locations. So it is by virtue of this image also it is called radial distribution system. What is the disadvantage of the radial distribution system? Advantage is that it is simple, and since there is only one path, the cost of infrastructure, the commissioning cost is minimum. As required, less infrastructure, less number of transformer, less number of poles, less number of circuit breakers, insulators, etc. So the commissioning cost is low. What are the disadvantages? Disadvantage is less reliability. As I told earlier, if there is a disturbance in that single path, then the customer will not get the supply. The second disadvantage is that since the distributor is fed from only one end, the customers who are near to the distribution transformer and the customer who are at the far end of the distributor have voltage fluctuations with load variations. Okay, so the customers who are at the beginning of the distributor or who are at the far end of the distributors will suffer from high voltage and low voltage respectively. Okay, so in this radial distribution system, the voltage profile to the customers is poor. Okay, so for whom we prefer the radial distribution system? We prefer radial distribution to the customers from whom we'll get less revenue. Okay, preferred for less revenue or the customers who pay less tariff customers. Normal public. So radial distribution system is given to normal public who give less tariff, less electricity energy charges. Okay. The second is ring main system. So in ring main systems, there exists two paths between the feeder of supply and the customer. Here there exists two paths between the feeder of supply and the customers in this system. Okay. In this system, the primaries of the distribution transformers form a loop. This loop circuit starts from the substation bus bar and makes a loop through the area to be served and return to the substation. Okay. So in ring main system, there are two paths from the major source of supply to the customer, and here how the ring system is developed. The primaries of all distribution transformers in that area form a loop. This loop starts from the substation and goes through the area where it has to provide the service and return back to the substation. What is the advantage of ring main system? It is more reliable since there are two paths of supply, so reliability is more. Less voltage fluctuations at the terminals of customers, that is better voltage profile, because as the distributor is fed from both ends, the voltage drop will be minimum, the voltage fluctuations will be minimum in the ring main system. Disadvantages is that it requires more cost to commission the ring main system, because it requires more distribution transformers, more circuit breakers, more conductors, more poles, etc. The commissioning and the initial cost is more. So for whom will prefer the ring main system? We prefer to the customers who give us more tariff and the loads which are very much essential, like hospitals will have ICU rooms, so and traffic control room, police control room. Okay, so this system of distribution is preferred for the customers who pay more and for the loads which are criticals like hospitals, control room, etc. Now if you can see in this image of a ring main system, ring main feeder, suppose this is a 11 kV, let us assume it is 33 kV bar 11 kV substation, from where 11 kV feeder is starting. So these are all the rectangular boxes are circuit breakers. The rectangular boxes are circuit breakers, and this is all these are the 11 kV bar 415 volt transformers which are supplying to the respective locations. Now if you can observe that 11 bar 415 volt distribution transformers. So here if there is any interruption in this path, let us say if there is any disturbance in this path, the electricity can be fed from the electricity to the customers can be fed in this path. Okay, so likewise the ring main system, the reliability is more because there exists two paths. If there is any disturbance or fault in one of the paths, the electricity can be fed to the customer in other path. The normal electrical circuit diagram that we use for ring main system is this one, where here it is the source and these are loads. So there exists two paths of supply to the load. Suppose this is the first path where this load can be fed, and there is one more path, this is path number 2, from which this load can be fed. This is a common diagram that we use to explain the ring main system. Next is interconnected system of distribution system. Interconnected distribution system. Here it is same as the ring main system, but the feeder, that ring is also energized by two or more than two sources. In the previous case, if you observe, this complete ring is energized by only one source. This is the source point. Okay, so if this ring is energized by two or more than two sources, then it will become an interconnected system. As you can see here, the ring that we have seen in the previous case, it is energized by two sources. This is source 1 and this is source 2. So the two sources are feeding the power to this ring. So with this, what we are going to achieve? We are going to achieve further more reliability. So interconnected system has following advantages. What are those? It increases service reliability. It has more reliability than ring main system, and any area fed from one generating station. So during peak loads, if source 1 is exhausted its capacity, then there is no need of load shedding. We need not power cut. We need not shed some of the load. Then we can take supply from source 2 and we can feed the loads. So this system of interconnected system will be more helpful when during peak load situations, because if the capacity of one of the generating station or one of the source is exhausted, then we can supply energy from the source 2. So with this, what we are going to achieve? This reduces the reserve capacity and increases the efficiency of the system. Now, what is voltage drop in AC distributor? Let us consider a distributor which is fed from one end. This is the source. Let us call this point A and this as point B. Now, the impedance of this one is, let us say the impedance of this one is Z1, this is Z2 and this is Z3. The loads, let us call this one as I1 at an angle minus phi1, I2 at an angle minus phi2, and let this current to be I3 at an angle 0. So let us consider a AC distributor which is fed from source at one end. Let Z1, Z2 and Z3 be the impedance of this branches. The current tapped here be let I1 at an angle minus phi1, I2 at an angle minus phi2, I3 at an angle 0. Then the total current that is flowing through the impedance Z1 is how much? It is carrying the total current of I1 at an angle minus phi1 plus I2 at an angle minus phi2 plus I3 at an angle 0. So this total current will flow through the branch Z1. Now what is the current that flows through branch Z2? Branch Z2 only carries the currents I2 and I3. This is I2 at an angle minus phi2 plus I3 at an angle 0. What is the current that flows through branch Z3? Only I3 at an angle 0 flows through branch Z3. Now the voltage drop in the distributor is how much? Voltage drop is equals to VA minus VB, that is equals to, what is this voltage drop? We have to calculate Z1 into the total current flowing through this one, I1 at an angle minus phi1 plus I2 at an angle minus phi2 plus I3 at an angle 0 plus Z2 into I2 at an angle minus phi2 plus I3 at an angle 0 plus Z3 into I3 at an angle 0. So this is the total voltage drop in this particular AC distributor. So we need not remember any formula, just I'm explaining how to calculate voltage drop in an AC distributor. Okay. Next, voltage drop in a DC distributor. Here we have considered a DC distributor which is fed from the source at one end. Let the resistance of this branch is R1, R2, R3 and this is R4. Let this point is A, point is B. Let the current is I1, I2 and I3. All are DC currents. Now, what is the current flowing through resistor R1? Resistor R1 carries the total current I1 plus I2 plus I3. Now I1 is being dropped here. What is the current flowing through R2? I2 plus I3. What is the current flowing through R3? It is only I3. What is the current flowing through R4? 0, because there is no load connected. So it carries 0 amperes. Now if you want to calculate the voltage drop in the distributor, voltage drop becomes how much? That is equals to VA minus VB. That is equals to how much? R1 into I1 plus I2 plus I3, R2 into I2 plus I3 plus R3 into I3 plus R4 into 0. This is how you calculate the voltage drop in case of a DC distributor. Now, the third case is uniformly loaded distributor. What do you mean by uniformly loaded distributor? Again we have considered a distributor which is fed from one end. This is the source. Let this point is A, point is B. Now this distributor is uniformly loaded. What do you mean? The current tapped per unit length is constant throughout the distributor. To understand this one, suppose the total load of this distributor is say 100 ampere. The total amount of current that is tapped from this distributor is 100 ampere, let us say. Now, what will be the current at point A? The current at point A will be 100 ampere because the total current is emanating from the source. Now, what is the current in the midway? The current in the midway will be how much? Because the current is uniformly tapped, at the midway you have a current of 50 ampere. At midway you have a current of 50 ampere. And what will be the current at the end? It will be 0 ampere. Okay. So, after 1/4, what will be the current in the distributor? 75 ampere. At 3/4, it will be 25 ampere. So, a uniformly loaded distributor is the one where the current tapped per unit length is constant. Okay, this is the uniformly loaded distributor. In this case, if capital R is the total resistance of distributor, capital X is the total reactance of the distributor. Let cos phi be the power factor of load. That means the power factor of the load is constant, which is cos phi. Let small I be the current tapped per unit length. Let small l be the length of distributor. Now capital I, that is equals to small I into L, is the total load on the distributor. So if you know all these parameters, what are the parameters we have discussed? Capital R is the total resistance of this distributor between A and B. Capital X is the total reactance of the distributor. Cos phi is the power factor of the uniform load that is being tapped from this distributor. Small I is the current tapped per unit length. L is the length of distributor. Then capital I, that is small I into L, is the total load, total current that is being tapped from this distributor. Then voltage drop in uniformly loaded distributor which is being fed from source at one end. Suppose this is source point, this is A, this is B. Then voltage drop VA minus VB is given by what? So since we already know the parameters, we can directly write I into R cos phi plus or minus X sin phi by 2. So the total voltage drop becomes mod VA minus mod VB is equals to I by 2 into R cos phi plus or minus X sin phi. So plus sign is used for cos phi lag loads, cos phi lagging loads. Minus symbol is used for leading loads. Minus phi is used for leading loads. Understand? So very rarely we'll see capacitive loads. So most of the times we see the inductive loads. So plus is the symbol that is used for lagging loads, that is inductive loads. Minus is the symbol that we should use for capacitive or leading loads. Understand? If the distributor, uniformly loaded distributor, is fed from both ends, this is point A, this is point B, it is source 1, this is source 2. Okay, now out of the total current, I by 2 current will flow from source 1. Half of the current, that is I by 2 current, will flow from source 2, and both these currents will become 0 at the midpoint M. So this source 1 will feed half of the distributor from A to M. Source 2 will feed from half of the distributor from B to M. So both the currents will become 0 at the midpoint. Now, where the voltage is the least, where the potential is least at the distributor, the potential is least at the distributor at a point M. So in this case, the voltage drop, in distributor is how much? VA minus VM, that is equals to VB minus VM. So it will become how much? From the same parameters, if you do, it will become I by 8 into R cos phi plus or minus X sin phi. So it will become 1 by 4 times that of the voltage drop in the previous case. Previous case it was I by 2. In this case it is I by 8. Why? Because now the total resistance where the current is flowing is becoming what? R is becoming R by 2. Why the change? R is becoming R by 2. X is becoming X by 2 because the current is only flowing in the half of the distributor and I is becoming I by 2. If you replace these terms in the previous equation, you are going to get this value. Okay. Suppose if it is a DC distributor, that is being fed from the sources at both end and the load is uniformly distributed, then voltage drop will become how much? The voltage drop in this case, that is VA minus VM, that is VB minus VM, will become how much? It is I by 8 into, what is the power factor in DC system? Unity. And what is the reactance? What is the inductance in DC systems? In steady state DC circuits, your inductance is 0 and your reactance is 0. So it is simply IR by 8. Why? Because in DC steady state circuits, power factor is how much? Cos phi is unity and your inductance is short circuited. So your inductance value is 0, your reactance value is also 0. So similarly, even in this case, had it been a DC distributor which is fed from source at one end, the voltage drop would have become, that is VA minus VB, become I by 2 into R, because cos phi is unity, reactance in DC circuits is 0. Now let us come to the questions. The selection of size of conductors for a distributor in a distribution system is governed by, so the selection of conductors in distributor is mainly governed by what factor? It is mainly governed by voltage drop, because in a distributor we have to provide proper voltage profile to the customer. So the size and the length of distributor is mainly governed by the voltage drop criteria. A single phase AC distributor supplies two single phase loads as shown in the figure. The voltage drop from A to C is. So what are the current? The current 30 ampere at 0.8 power lag, we can write it as 30 at an angle minus 36.86 ampere. And the second one is, we can write it as UPF current, we can write it as 40 at an angle 0 ampere. So what is the total current flowing in the branch AB? The total current that is flowing in branch AB is 30 at an angle minus 36.86 degrees plus, what is the other current? 40 at an angle 0. Now what is the current flowing through the branch BC? The current flowing through the branch BC is only one current, 40 at an angle 0. Now voltage drop VA minus VB will be how much? What is the impedance of branch AB? J 0.25 into, what are the currents? 30 at an angle minus 36.86 plus 40 at an angle 0. What is the other current? What is the other impedance? Impedance of branch BC? J 0.35 into 40 at an angle 0. If you do this calculation and calculate the magnitude of this one, you are going to get how much? So this voltage drop will become 30.3 volts. So the nearest option is option C is the right option. Now if you see the second question, a DC distribution system is as shown in the figure with load currents as marked. The two ends of the feeder are fed by voltage sources. This is one voltage source is Vp, the other voltage source is Vq. The difference between these two, Vp minus Vq, is 3 volt. The value of the voltage Vp for a minimum voltage of 220 volt at any point along the feeder is. What is asking? This is a DC distributor that is fed from two sources. One source is feeding at point P, the other source is feeding at point Q. Now, the minimum voltage along this distributor is 220 volt. The minimum voltage along this distributor is 220 volt. Now he is asking us to calculate the voltage at point P such that the distributor minimum voltage is 220 volt. To approach this problem, what is the total load on the distributor? The total load on the distributor is how much? 10 ampere plus 20 ampere plus 30 ampere plus 15 ampere. It all boils down to how much? 50, 60, 75 ampere. 75 ampere is the total load on the distributor. Now, let us assume the source at P is supplying a current of I ampere. Then what is the current supplied by source at Q? The remaining current, that is 75 minus I, is being supplied from the source at Q. Okay. Now, out of this I, how much current is flowing through the load which is connected to P, 10 ampere. Now, what is the current that is flowing through 0.1 ohm? The current that is flowing through 0.1 ohm resistor is how much? I minus 10. Likewise, what is the current flowing through 0.15 ohm resistor? It is I minus 30. Current flowing through the 0.2 ohm resistor, 1 I minus 60. Okay. Now, what is the voltage drop given? Vp minus Vq, he has given it as 3 volt, which implies this voltage drop is equals to voltage drop along the branch that is connected between P and R and S plus S and Q. What is the voltage drop of the branch connected between P and R? 0.1 ohm into what is the total current? I minus 10. Similarly, the voltage drop of the branch RS is 0.15 into I minus 30. Similarly, S and Q is I minus 60 into 0.2. This should be equal to 3 volt. If you do the simplification, what you are going to get? 3 volt is equals to 0.45 I minus 1 minus 4.5 minus 12. So which implies how much? 0.45 I is equals to 20.5 volt, which implies I is equals to 20.5 divided by 0.45. So what is this value? This value is 45.55 ampere. So source at P is supplying how much current? Source at P is supplying a current of 45.55 ampere current. Similarly, source at Q is supplying the remaining current. Remaining current will be how much? 29.45 ampere. So these are the two currents supplied by the source at P and Q respectively. If you know what is the current that is supplied by source at P, the current supplied by the source at P is how much? 45.55 ampere, and source at Q is supplying 29.45 ampere. Let us see how this current is distributed. Out of this 45.55, 10 ampere is flowing here. So what is the current flowing through the branch PR? 35.55 ampere. And again out of this 20 ampere is getting dropped here. So what is the current flowing through RS branch? 15.55 ampere. Now coming to this one, out of 29.45, 15 ampere is flowing through the load at Q. The remaining current is how much? Remaining current is 14.45 ampere is the remaining current that is flowing from Q to S. So from all this one, what is the least potential point? Least potential points. The point which is having the least voltage on the distributor is S. Why? In DC circuits, current always flows from higher potential to lower potential. So it is obvious that since the current is flowing from Q to S, Q is at higher potential than S. Similarly, R is at higher potential than S. And likewise, P is at higher potential than R. So in the problem, what is the voltage of the least potential point? He has given it as 220 volt. 220 volt. Now, with Vs voltage as 220 volt, we have to calculate Vp. So what is Vp? Vp is equals to Vs plus drop in branch RS plus drop in branch PR. Okay, so what is Vs? 220. What is drop in branch RS? How much current is flowing through this one? 15.55 into 0.15. What is the drop in PR? 35.55 into 0.1 ohm. So this total voltage will become how much? Voltage will become 225.89 volt. So P is at a potential of 225.89 volt. Now let us take the other question. A distribution feeder of 1 kilometer length is having a resistance but negligible reactance, is fed from both ends by 400 volt 50 Hz balanced sources. Both voltage sources are in phase. The feeder supplies concentrated loads of UPF as shown in the figure. The contribution of S1 and S2 in an 100 ampere current supplied at location P is. That is the question. So here there are two sources, S1 and S2. Both are in phase and the distributor is completely resistive. There is no reactance and all the loads are at a unity power factor. Okay. Now he is asking at point P what is the load connected? 100 ampere load is connected. Out of this 100 ampere, how much is contributed by source S1 and how much current is contributed by source S2? Let capital R be the total resistance of 1 kilometer distributor. Let capital R is the total resistance of 1 kilometer distributor. Now, what will be the resistances of these branches, individual branches? Then they will become how much? This will become 0.4 R because it is 400 meter. This will become 0.2 R. This will become 0.2 R and this will become 0.2 R. Okay. There is no reactance. Second point, let I be the current supplied by source 1. So the current that is flowing from source 1, let us call it as I. I is the current that is flowing from source 1. Now what is the total load on the distributor? Total load is the sum of three currents. It is 500 ampere. Total load is how much? 500 ampere. Then how much will be the current supplied by source at S2? current supplied by source S2 will become 500 minus I. That is, current supplied by source S1, we are calling it as I. Current supplied by source S2 will be how much? Will be 500 minus I. Okay. Now what is the voltage drop from point, let us call this point as A. Let us call this point as A. What is the voltage drop in the distributor? Voltage drop between A and B is how much? Because both the voltages are 400 and both are in phase, this will become VA minus VB will become how much? That is equals to VS1 minus VS2, whose value is 0, because at both point A and point B the voltage is 400 volt and both the voltages are in phase. So the voltage drop in this distributor is how much? 0. Okay. Now let us calculate the individual voltage drops. What is the voltage drop in this branch? 0.4 R into I. So the current I is flowing through this branch, and here out of I 200 is getting dropped. So what is the current flowing in this 0.2 R? It is I minus 200. Now what is the current flowing through? What is the current flowing through this branch of 0.2 R after P? I minus 300. And what is the current flowing here? In this direction it will become I minus 500. I minus 500. Now if you calculate the voltage drops, VS1 minus VS2, it will become how much? 0.4 R I. And what is the voltage drop here? 0.2 R into I minus 200 plus 0.2 R into I minus 300 into 0.2 R into I minus 500. This is the total voltage drop in the distributor from the above assumptions. This value will become 0. This is equals to, it all boils down to how much? It all boils down to Ri is equals to 200 R. Okay, so I value will become how much? 200 ampere. So current supplied by source S1 is how much? 200 ampere. The current supplied by source S2 is how much? 300 ampere. Okay, now out of this 200 ampere that is supplied by source S1, the total 200 ampere is being taken by this first load. Okay, now both these loads, both this load 2 and load 3 are being fed by whom? Source S2, are being fed by source S2. So at point P, source S1 is contributing how much? 0 ampere. Source S2 is contributing how much? Total 100 ampere. That is the answer. Okay, option D is the right option. Source S1 is contributing 0 ampere, S2 is contributing 100 ampere. Let us come to the last question in this lecture. A single line diagram of 4-bus single source distribution system is as shown. Branches E1, E2, E3, E4 have equal impedances. The load current value is indicated in the figure or in per unit. Distribution company policy requires radial system operation with minimum loss. This can be achieved by opening the branch. So now what is telling? It is a ring system of distribution that is given in the question. So the company wants to convert this ring system of distribution into radial system of distribution. So he's asking our suggestion. See, in this ring system, if you remove any branch, it will become a radial system. It will become a radial system. So we have to remove the branch such that the total losses in the distribution system are minimum. The total losses in the distribution system are minimum. That is the question. Okay. So, to minimize the losses, the maximum current should flow through least minimum path. So the basic idea or the simple technique that will reduce the losses is the maximum load should flow through the minimum path. So how we can ensure that the maximum load only flows through the minimum path? What is the highest load? Highest load is 5 ampere load. This is the highest load. So I want this 5 ampere to flow through minimum number of branches. So to ensure it only flows through the minimum number of branches, if I remove E4, then the total losses will be minimum. That means if you remove E4 branch, this ring system will be converted into radial system, and in that radial system, the transmission losses will be minimum. So if you ensure this logic, then you will minimize the losses. Likewise, the highest current is 5 ampere. To ensure it only flows through one branch, we are removing E4. Now in the first case, now let us come to the other method where we are doing stepwise procedure. Let us remove the first branch and calculate the losses. If you remove the first branch, what are the currents that are flowing? Now we can see what is the total load. 5 plus 7 plus 1, 8. So it is coming from source. This 8 ampere should flow through E2 because there is only one path. So out of 8, 5 is getting dropped here. Here 3 ampere will flow and here 1 ampere will flow. Now let capital R be the resistance of each branch. Now the total losses in this case will become how much? So the resistance of each branch is R. So 8 square into R plus second branch current is 3 square into R plus 1 square into R. What is the total losses? 64 total losses in this case. Okay. Now in this case, let us remove branch E2 and let us calculate the losses. Again, what is the total load? 8 ampere. So here branch E1 carries 8 per unit. Let us call ampere for our convenience. The second branch will carry how much? 7. The third branch will carry how much? 5. So if you calculate losses, total losses is how much? Total losses will become 8 square into R plus 7 square into R plus 5 square into R. 138 R. Now in the third, let us remove branch E4. In this case, what it will become? The total current in branch E2 is 5 ampere because and in branch E1 it is 3 ampere and in E3 it is 2 ampere. So total losses will become how much? Total losses will become 3 square R plus 5 square R plus 2 square R. So what is the value? This will become 38 R. If you remove branch E3, the total current should be how much? It would be 7, 2 and 1. So total losses will become 7 square R plus 2 square R plus 1 square R. Total value will become 54 R. So if you compare the losses in each case, so in first case, what are the losses? In first case, the losses are 74 R. The second case losses are 138 R. If you remove branch E2, if you remove branch E3, the losses are 54 R. If you remove branch E4, the losses are 38 R. So which is the best configuration? That means if you remove branch E4, If you remove branch E4, the given ring system is being converted into radial system with minimum losses. That's what we have explained in the earlier logic. Thank you very much.